Welcome back. The objectives of this video are to introduce instantaneous rate of change and the concept of the tangent line. Instantaneous rate of change is formally developed more in calculus, but we're going to talk about that by calculating the average rate of change over really small intervals. And in calculus, we will talk about this as the concept of the limit. We'll talk about the limit as our x approaches some particular value. So here's our sample problem. Suppose an object is launched upward from a height of 120 feet with an initial velocity of 48 feet per second. The height of the object is given by this formula. So our output is the height and our input is t, or time. This problem asks us to find the average rate of change in the height of the object over the given intervals. So these given intervals of time. Our x values or our t values, we'd input those into our function. So you can put just 1 in for t and put that into your calculator and figure that out. Instead of just simply calculating the heights based on inputting the x values, I opted to use the table feature on my calculator. And what you do is you put the function in as if you're going to graph it. So I went into the y equals and I put the function in. And then we can go to the table set, which is above the window key, second table set. And I wanted to start counting at 1 because my range was from 1 to 1.1. And my change in table is 0.1. So I set that at 1 and my change in table is 0.1. And then I went to my table, and it gives me x's for every 10th beginning at 1. I know now that f of 1 is 152 is my height or my y value, and at 1.1 my height is 153.44. So algebraically, I do f of 1.1 minus f of 1 all over 1.1 minus 1, my change in y, over my change in x. And the 1.1 was 153.44 minus 152. And our average rate of change then is 14.4 feet per second. And then I simply repeat the process for problems or samples B, C, and D. So in this second problem, I need 1.01 in my table. So I can go back to my calculator, and I'll just change the table set. Instead of counting by 1/10, I'm going to count by 1/100th. And go to second table. And then it gives me 152.16 for my value for f of 1.01. For demonstration purposes, I needed some more significant digits instead of the 0.16, so I went 1.584, and that comes out to 15.84 feet per second. So filling in and completing the rest of the problems from 1.001 seconds to 1 second, we find that average rate of change. We use the table value or use our calculator or input things into the formula. We get these numbers, and we get 15.984 feet per second for problem C. And then for problem D, we put that into our calculator and calculate those values, and we get 16 feet per second. So you can see here that as we get closer and closer to 1 second, as that gets smaller and smaller and smaller, okay, we're getting closer and closer to 16 feet per second. So our limit here, as time approaches 1 second, we're approaching 16 feet per second. So using your rates from above, what is your estimate for the instantaneous rate of change? that would be at t equals 1 second. So at time equals 1 second, we can anticipate the rate of change of the height at that very second is 16 feet per second. So the big idea here is that we've got this particular curve, and we are picking 2 points. And what we're doing with those 2 points is we're taking them, so if like this is 1 second and this is 1.1 second, we're taking that point and we're moving that closer and closer. So the first secant line is going to give us one particular slope, and the next one, as it gets closer, gives us a new slope. And as we pick a third point even closer to 1 second, we get another slope, but that's even closer. And so what we're doing is we're getting closer and closer and closer to those 2 points, and that secant line is getting closer and closer to becoming a tangent line. So the closer that secant line becomes to a tangent line, the average rate of change gets closer and closer to becoming the absolute instantaneous rate of change. And when that secant line becomes a tangent line, then we have our instantaneous rate of change. So if that, maybe that blue line becomes our tangent line, and that's going to give us the instantaneous rate of change. Sample 6, they ask for each of the following functions, describe the average rate of change over the given interval as positive or negative. Try to do this without substituting values in. Well, x squared is just a parabola that looks something like that. That's supposed to be at the origin there. The vertex is at the origin. And we want to see what's happening between like x is 2 and x is 3. Well, that's going to be a tangent line might look something like that. So that is going to have a positive rate of change. Our function, our logarithmic function, log of x. If you know your logarithmic functions, which we may or may not have studied yet, that's going to go through that point of 1, 0. And we want to know what's happening between 0.01 and 1. So that's in here. Well, our tangent line, it looks like that also will be positive. In sample C, we have an exponential function, 1/2 raised to the x power, and an exponential function. If we put 0 in for x, anything to the 0 power is 1. So that is going to be a graph that looks something like this, and it's going to pass through 0 on the x, 1 on the y. And what's happening between -1 and 0? So if -1 is here, we're wondering what's going on like right there. And that tangent line has a negative slope. And in D, we have another parabola. We have a quadratic function here, -2x squared. So that parabola is going to open down. That guy's been shifted up 5 units. And so that parabola is going to look something like that. And we want to know what's happening between, say, 1 and 4. So that also, that tangent line has a negative slope. Let's take a deeper dive into the tangent line concept. The graph of f is shown at the right. The tangent line of f at x equals -3 is shown. We will prove that the tangent line here is the instantaneous rate of change. We just talked about that a second ago. Use the tangent line to estimate the rate of change of f at x equals -3. We'll only have this one point. It looks like the y value at -3 is about 3 1/4. We could use another point here. -4, 0 doesn't quite work. It's pretty close. It looks like we have a hash mark here at -2. So we will use -27. So those are going to be our 2 points, and we'll estimate the rate of change. So we'll do f of -2 minus f of -3 all over -2 minus a -3. Well, we've got our ordered pairs. The output for -2 is 7 minus 3 1/4 all over -2 plus 3. And we get 3.75 is our estimated rate of change at that point. B says to sketch tangent lines to F at the 3 points shown in the graph. So we've got 3 different points here. We want to sketch the tangent lines. I'll do those in blue. I'll do the best I can. So that wasn't a real good tangent line. That might be a little bit better. We'll move that guy over to something like that. And down here at that inflection point, we've got a tangent line there. And then I'm going to end up moving this tangent line too, I bet. Yeah. We'll take that guy and we'll move that over. All right, and we got that guy here, something like that. So we've got a real steep positive slope here at the far right at around 4, it looks like, for x. And when x is -1, we've got a pretty good steep negative slope, and we've got a slope of 0 here at 2. So describe the behavior of the graph of f and the relationship at the rate of change at x equals 2. Well, we just talked about that. That's a horizontal line. So the slope of that is 0. So the slope equals 0. So our rate of change at 2 is 0. So real quick summary of behavior and rates of change. If the rate of change is positive, or the slope of positive is positive, our graph is increasing. If the slope is negative, our graph is decreasing. If the slope is increasing, this is a question of concavity. So we are concave up. Sometimes I like to do just that. And if the slope is decreasing, we are concave down. So you'll see me just draw a picture like that. In sample 8 here, we've got a graph at the right. The graph is increasing and concave up because the rate of change is positive and G is increasing. And that wraps up our introduction to instantaneous rate of change and the tangent line. And we'll get some more practice with this when I see you in class.